need to come read the is it on the control? Not I don't lie. I know the experience of having it. Why don't you know about that? Yeah, and I go pee on which one's presentation? That's right. Right? Let's use our brain for a color, and then we'll see what happens. You know, it's like I remember looking.
It's not this one. This one?
Well, no.
So
Control. That's it. That's I couldn't remember which letter it was.
It rotates left.
It's fine. Not control that. Control shift.
There'll be something on
Yeah.
the screen.
Yeah, but there's no view. I don't see view at all.
That's when this opens up.
Are you trying to go full screen?
Yeah.
Yeah.
Yes.
I think it's at the bottom right. If you go back to
Okay.
in section view.
That's fine.
No.
There you go. That's the problem with all my graduate students.
Yeah. Not fit for AI if I can't make it and put it in the presentation, but some.
So our next speaker is John Cutler, and he will talk on alternating number of independent sets.
Great. Yeah, thanks very much, Sandra. And thanks for organizing the workshop again this year. Thanks for everybody for coming. I volunteered to give a 15-minute talk, and I was somehow given over slot. So that's my goal, is to go a little bit slowly. So if you have any of your questions at any time, please interrupt. Even if those questions are speed up because you're going way. That's more than likely. Okay, so all of this is joint work with Nick Kale here and former master's student of mine, Yolanda. And a lot of the research here is a little bit older, so it definitely predates AI. Okay, so I'm going to be talking about the alternating number of independent sets in the graph. For me, the easiest way to come at this problem is to think about the independence polynomial. Like I said, I'm going slowly, so I'm going to introduce this very gently. So the independence polynomial is just the generating function for the number of independent sets in the graph. So one way of thinking about it is you just find it as this polynomial, when the coefficient of x to the k is the number of independent sets of size k. So I'm going to use that notation, I sub k of g for the number of independent sets of size k in a graph. Alternatively, if you there are some other ways of thinking about this thing. So one alternative way of thinking about it is you could just sum over all of the independent sets in your graph and take x to the size of that independence. Okay, and then you're just clumping. This is just clumping together like terms. All right. So and maybe in an effort to go slowly and make sure everyone's had enough tea, just as a sort of a warm up. Of course, for any graph G, if I want to know I sub 0 of G, then that number is 1. If the empty set counts as an independent set. If you want to know about I sub 1 of G, then it's just the number of vertices. We're thinking about loopless graphs, simple graphs with no loops. So every vertex by itself counts as an independent set. So I sub 1 of G is just the number of vertices, and I sub 2 of G is just the number of non-edges. So it's n choose 2 minus the number of n, right? Okay, so right, and even more warm up. So although some of this will be useful a little bit later as well. So if you want to know, so here are the independence polynomials of basic graphs. If you want to know the independence polynomial of any complete graph on n vertices, then of course, if you take any set of size at least 2, it's not going to be an independent set. So what you're only going to get the empty set and the single vertices. So you get a linear polynomial, it's just 1 plus nx. On the other extreme, if you want to know about the independent polynomial of the empty graph, and of course, every subset is independent, and so you're just summing over all possible sizes of independent sets. Taking the number of subsets of size k multiplied by x to the k, and if you apply the binomial theorem, you can just rewrite that as 1 plus x to the n. Or if you want to take the independence polynomial of the complete bipartite graph, then of course you're only going to be able to choose independent sets entirely from the right-hand side and entirely from the left-hand side. You get 1 plus x to the r, 1 plus x to the s, but then you count the empty set twice to get the subtract part of account for that. All right, cool. Okay, so here's a useful fact. The independent polynomial is multiplicative on disjoint unions. So technically speaking, what does that mean? That means that if you've got two graphs with disjoint vertex sets, and you want to know, and you know the independent polynomial of each of the two graphs individually, then you can just multiply the independent polynomial. I mean, that's, if you think about our earlier two different forms of the independent polynomial, those are, you can use either one of them to justify it. One of them can take this convolution. What are your independent sets in the disjoint union? They're just going to be subsets over here, not subsets of D and subsets of H. And so together. Or alternatively, if you want to think of if you want to derive the independence polynomial of the empty graph from the fact that you know that the independent polynomial of a single vertex is 1 plus x, then of course that's just a bunch of disjoint unions, and so you get this other way of thinking about 1 plus x to the n being the independent polynomial of the empty graph. Okay, so hopefully everyone's bored at this point, but okay. So at least one person. Good. So what are we interested in? We are interested in evaluating the independence polynomial at some values. Some values are really boring to evaluate. So for example, if you evaluate any independence polynomial at 0, then of course you're knocking out all of the interesting terms and you're left with just the empty set, so you get 1. A much more interesting one is if you plug in 1, then you get, what are you doing? You're summing up I sub k for all values of k, and so you're just getting the total number of independent sets in your graph. This is an interesting invariant graph with lots of cool questions floating around there, but that's not the subject of this talk. So you can think about other values of x. I'll mention some other values at the very end of the talk, but for now, there's only going to be one value that we're interested in. That's plugging in negative 1. So this has come up in a variety of different settings and in a variety of different fields. So I won't be able to answer questions about this, but one place it comes up is in algebraic topology, and take a sequential complex, and if you are interested in its so-called reduced Euler characteristic, then if you think about the independence complex, that there is one of these things that corresponds to the independence complex of the graph, which is just the complex that corresponds to the independent sets in the graph, then the independence polynomial at -1 corresponds to this reduced Euler character. Okay, but again, I'm not an expert in that, so I can't really say much more than that. Purely from a combinatorial point of view, it's not such an unnatural thing to consider, actually, because what are you doing? I mean, if you think about it just in the independent polynomial, you're just alternating signs here. That's why it's called the alternating number of independent sets. Or if you gather together all the positive terms and all the negative terms, all the even-sized independent sets are, of course, positive, and all the odd-sized independent sets are negative. So what you're doing, you're just taking the total number of even-sized independent sets, and then you're subtracting the total number of odd-sized. That's the alternating number of independent sets in a graph. Okay, is that clear to everyone? Is it cool? Good. So that's the object we're going to be studying. So I will generally refer to it as this, although I will probably call it the alternating number of independent sets in the graph, or maybe just the alternating number if I get lazy. Okay, so the history of the problem. I mean, so I should have said this earlier, but I'm giving sort of a personal history of this problem in terms of how I found out about various results, and I'm doing it chronologically from my perspective, so it's a bit of a selfish talk, but it gives you maybe it tells a better story than if I did it chronologically. So So Angstrom, coming at it from this algebraic topology point of view, was able to, among other things, prove the following bound on the absolute value of the independent polynomial. He proved the bound in terms of this rather strange graph invariant called the discycling number, which I hadn't heard of until I saw this result. The discycling number is the minimum number of vertices that you need to remove from your graph in order to make it acyclic. Okay, so if you've got a bunch of disjoint cycles, disjoint union of a bunch of cycles, then you're going to have to remove one vertex from each one. Whereas if you have something like the friendship graph, right, which is a bunch of triangles share a single vertex, then the discycling number of that graph is just one, right? So it's it is a nice graph invariant. It is NP complete to compute, I believe. Yeah, and what he was able to show was that in absolute value, the independent polynomial of -1 is at most 2 to the discycling number.
So you remove vertices?
Remove vertices, yeah, exactly.
With the each.
Yeah, exactly. Yeah, so when you remove the vertices, you remove all these. So a tree of the discycling number is 0, right?
What if you just remove the edges of the I mean, does it have to be the vertices? What if you?
Yeah, I mean, you can think about other invariants that are about edges, but this one's going to be about vertices. That's the right thing. Well, in fact, in this the way that he proved it, this was the invariant that we were.
The discycling number for edges is very easy probably now because you have to make every component a tree.
Yes. In fact, yeah. So in fact, if you're connected, then you know exactly. It's just the number of edges minus that -1, right? Quantity n minus 1, right? So this is a more robust graph invariant. Yeah. Okay. So what am I doing next? Yeah. So I'll come back to talk about the robustness or the sharpness of this result in just a second. But before I do that, I actually want to give maybe not the entire proof, but at least all of the components of the proof. So the original proof by Angstrom is too complicated for me to use the sweep Morse theory, and it's actually a special case of a much more general result that he was able to prove. But Levitt and Mandrescu were able to reprove the bound using elementary methods. The key tool is the following tool, which is a recursion that's due to Gutman and Harari. I don't have a year there, but a while ago, but years ago, something like this. So, and what did they show? They showed that the independent polynomial has this recursion, which is not hard to show. What is it? It's just you take any vertex in your graph. If you want to know the independent polynomial of the original graph, you remove a vertex, and then you multiply x by the independent polynomial on the graph with the closed neighborhood removed, right? So that's the vertex and all its neighbors. And so what does that correspond to? Roughly, these things correspond to independent sets that don't contain that vertex B. These things correspond to independent sets that do contain the vertex B, and this little factor next is all those things are bumped up by the fact that you're including one extra vertex, namely the vertex. So with this recursion in hand, of course, you can just plug in -1, and then that x just becomes constant. So
neighbors of V include V? No.
Well, in this case, so the closed neighborhood, there's something called the open neighborhood, which is just doesn't include the vertex, but the closed neighborhood includes the vertex of V as well. So this here you're removing from G both V and all of this. And that's because if your independent set contains V, it can't contain any of its neighbors. And so you just delete all those things. You'll get independent sets. The questions, is it okay? So if you plug in -1, you just this x becomes a minus. All right, good. So now I'm going to prove, or at least give you a hand-waved proof of Angstrom's bound. It's as soon as you've got the recursion, there's nothing here. So like there's a bunch of symbols and words here, but like if I told you it was induction, you just all write down exactly what you think you write down. So there is a little bit of faffing around to do with the base case. Base case has to do with forests. You can think about that when I'm going way too slow later in the talk. But the inductive case is easy. You just pick a vertex that decreases the decycling number that has to exist, and then you just apply induction, right? And I guess you apply the triangle inequality on induction. So it's as easy as you could possibly imagine it to be. Yeah, but we'll come back. I mean, I've skipped over the base case here, but I will say the base case here is not hard. We'll see later in the talk that the place where the base case is hard. All right. So now, being combinatorialists, we of course have another question, which is, how good is this result? Is it sharp? And it is sharp. So just as an example, if I take the disjoint union of few copies of a triangle, right, then it's multiplicative, like we talked about on components. We know that each triangle has independence polynomial 1 plus 3x. So the independence polynomial of few copies of K3 is just 1 plus 3x cubed. And since all those cycles are disjoint, you have that the cycling number is q, right? You have to remove a vertex from each of the cycles. So that gives us a graph whose the cycling number is q and whose independence polynomial -1 is as large in modulus as this bound is, right? So it's -2 to the q, and absolute value is 2 to the q. So it's 2 to the decycling number. But Levitt and Majewski asked a sort of even more robust version of sharpness, which is not only can I get to the extreme, but can I get everywhere in between the two extremes, right? So this is a bound. Levitt and Majewski's or Engström's result is a bound on the absolute value, right? So that's telling us that the independence polynomial at -1 is somewhere between -2 to the decycling number and +2 to the decycling number. And they asked, can you attain with some? Is there some graph with the cycling number? Now I've switched it, sorry, to k, the cycling number k, so that I can attain every single number between -2 to the k and +2. Does that make sense? So this is a stronger version of sharpness. And with Nate forever ago, we were able to show that we were able to construct graphs that attain these numbers. And since I've got time, then I'm going to show you the constructions. The constructions are not so hard, but I think they're kind of nice. So the constructions depend on two operations, and then the recursion, of course, that I talked about before. So before I show you the two operations, I'm going to just introduce a little bit of notation. First of all, I'm going to give our graphs roots. This is sort of irrelevant. It's just going to tell me where I'm going to apply my recursion. So it's just going to be the vertex that I'm actually removing and then remove its neighborhood. So the root actually is, in some sense, irrelevant. But of course, if I take this, if I artificially impose a root on it, then I'm going to do my recursion on that root, right? And if these two things are just numbers. So if this first one's A, I'm going to call it A, and the second one's B. Then I'm going to introduce this little bit of weird notation where I'm going to say the independence polynomial at -1. It is just A minus B by the recursion, but I'm going to introduce this notation, this bracketing notation, where the positive term is A and the negative term is B. All right. So this bracket is nothing other than just a fancy way of writing down A minus B. Okay, so it's just a bookkeeping device. So don't worry about it too much. I could probably do it without it, but I'm somehow used to it. So it's helpful for me at least. Okay, so here's the first of the operations that's going to allow us to get these constructions. The first one we call pasting, and it looks like we're pasting things, right? So I take two rooted graphs. I've made the roots on as leaves here, but they don't have to be leaves. And how do we paste? We paste together by identifying the two roots. That's all we're doing. But there is a nice formula for the independence polynomial of after I do this pasting. So what happens? Well, if I know the bracket here, this tells me the independence polynomial. This graph over here is A minus B. This one's C minus D. Then if I look at this one, I can do my recursion on this new identified vertex. What happens? Well, but first I remove that vertex. And what do I get? I get this thing and this thing, right? But this potato over here is just GB minus B. And I know the independent polynomial of that is A, right? And this one is HW minus, it's form a root W. So that's just C, right? And so if I want to know, and then how do I combine those things? They're disjoint unions, so I multiply, right? And similarly, if I remove this vertex and its closed neighborhood, right? Well, this vertex and its neighbors, then I'm just removing this vertex and its neighbors over here, this vertex and its neighbors over here, right? That's the second term of the recursion, right? So I get a B term here, over here, and a B term over here. And again, I've got a disjoint union, so I multiply them. So if I want to know, if I know the independent polynomials or the brackets of these two graphs here, these two rooted graphs here, then I can work out the independent polynomial and even the bracket. It's nice form. I just multiply term by term. Okay. Yeah. So, and then the other operation is I'm going to just hang a path. Actually, I'm just going to extend a path, or one edge at a time, extend a path off of the root. Okay. So let's just think about doing it once. If I know the bracket of GB and I extend once, then what does my recursion do? I remove that new root here. I'm pushing the root along the extension as well, right? So remove that vertex there. I end up with just GB. What's the independent polynomial of GB? It's just A minus B. That's what this bracket means. And then if I remove both the new vertex, the extended vertex, and its closed neighborhood, I'm only removing the old root, right? And so that corresponds to the old first term. And so I end up with the first term being A minus B and the second term being A, right? And then I can just rinse and repeat that process. So the next one, what am I going to do? I'm going to take the difference of these two things. That's A minus B minus A, which is minus B. And then this roots over to the, and continue, okay? All right, so those are the two operations we're going to need. And then with a little bit of work, we can actually get the sharpness result completely. Okay, so I'm only going to go from, well, I'll show you how you can use these things to get the sharpness result for the discycling number 0 and discycling number 1. Then if you see that, you can do the rest of it yourself. So for 0, I mean, there's a little bit of messing around here at the beginning. If I start out with just a single vertex, then we know that its independent polynomial is 1 plus x. So if I plug in -1, I get 0. If I get k2, then I get -1. But what I really care about is its bracket, because I want to start extending, right? If I have a k2, and I don't care which one you decide is the root, if I remove it, then I get 0. That's from k1. If I remove both the root and its neighborhood, I remove everything, so I end up with the empty graph. The empty graph is going to have independent polynomial 1. Okay, so the bracket of k2 is 0, 1. And then I can just start extending, right? So what does extending do? It takes the difference of these two things, right? And then moves the 0 over, and then I can extend and extend, right? Extend and extend, do the same process. Difference, move over, difference is 0, move it over, and I get all the possible values, right? So if my discycling number is 0, then I'm between +1 and -1, and I'm taking all into two. Okay. So what happens when I move to discycling number 1, right? So how do I keep going? Well, I'm going to use K3s, so triangles, to start. So now I need to hit every value between 2 and -2, right? So if I just use K3, think about K3, pick your favorite root, remove it, I get K2. If I remove both the root and its closed neighborhood, I removed everything, but the empty set. So this one gives me -1, as we saw on the last slide. This one gives me 1, as we saw on the last slide. Make the difference between -2. And then I can extend, right? So extend gives me difference, -2, move the -1 over, and difference of these two is -1, and move the -2 over. Okay? So, and now I have all the bits that I need. So I have all the constituent pieces. Now I'm going to start gluing things together in the right ways, and I'm going to be able to hit all those values between -2 and 2. So I reminded you here, here's my 2 extensions of my K3s. Here's my 3 extensions of K2s. Well, I meant to say this before. Extensions of K2s are of course, just paths, right? So I'm not doing anything. I'm just taking a bunch of different paths. I'm using this language. So I don't have to think about the independent polynomial, but we can do it this way. And then, like, these two things up here are giving me some 2s. These things down here are giving me some 1s and 0s, basically, with signs. And if I can rearrange them and line them up correctly, I can get everything I want, right? So I won't do all of these. Yep.
Sorry, can you just say again what the extension does to the bracket?
Yeah. So again, so if I go from here to here, if I can reach those, then what I'm taking the A minus, this is A and this is B. The first term over here is going to be A minus B, so it's -1 minus 0. That could be -1. And then the second term is the old A, so this gets scooched over the second slot, right? And then again, the difference of these two things is 0, and then this one scooches over this.
It's like the Cleveland algorithm.
Yes, something like this. Yeah. Much easier than that. Yeah.
Thank you.
Yeah. Does that make sense? Yeah. So, and the idea here basically is I'm trying to line things up correctly, right? So that I get things, big in the first term or big in the second term, and that gives me all of them things, right? So if I take K1, 3, that's this one up top there, and join it and paste it to K2, 1, and I'm just multiplying term by term, right? So I'm getting -2 times -1, that gives me 2, and -1 times 0, that gives me 0, right? If I take the difference of those two things, I get 2. There's my big one. And then rinse and repeat. I think I got these all right. I did these last week at some point. So K1, 3 with this one gives me -2, 1, 2 minus 1 is 1, right? And then this one I have to get a little creative. I'm taking some path. This is just a longer path. But if I take a long enough path, actually, if I take the right length path, I get 0, 0 as my bracket, and that knocks out everything. So that gives me a 0 value, and then I get this 2 things. I can do the same things with the opposite side and get the negative numbers.
And the subscript is just a root, right?
It's just that.
I doesn't depend on the.
So this I'm being a little bit confusing here. This subscript is the length or the size of my complete graph. But if I'm talking about and since everything's symmetric that I've written down here, I can choose any of the vertices to be my the root is just telling me which thing I'm recursing on, which vertex I'm recursing. So these subscripts are a little bit different than some of these that I had before in my leading graph.
Right, but when you have the independent polynomial, that subscript is just to help you make sense of the bracket in case you're using, right?
Yeah, it's telling me which vertex I'm recursing on, so that's just telling me what those two.
But the independent polynomial doesn't depend on
It does not. Yeah.
But then say again what the things here are, G?
These things are graph like this. This is just telling me it's K3, so it's a triangle, and this superscript is telling me how I'm choosing one of the vertices and extending off of that, right? So this looks like. So K3, 1 is the graph triangle with a pentagon on it, right? And it doesn't matter which. I'm being a little bit lazy here about which vertex I'm choosing, but it doesn't matter. So everything's.
And K1 is just a path.
Yeah. So K3, 2 is if I do 2, then there's an extra one. Stop extending. So once I've extended, I have actually made a choice as to what my root is, and so I'm extending off that. Okay. But it doesn't matter which one I choose, right? It's always going to go with the same thing. It may change the bracket, but it doesn't change the value. Okay. Cool. Other questions?
Sorry.
Yes. Yep.
The next K3, 1 and K3, 2, 1 and K3, 3. So where do you put the triangle then?
So this one, K3, 1 is here.
The one above that?
This one?
Yeah.
So this is this one. When I do these two, and you see I have a 0 in the first component of a second component here, and a 0 in the first component here. So when I multiply those two things, I get a bracket of 0, 0. And so if I paste that with anything, I'm going to get 0, 0. Right. So this is helpful to knock things out.
You always want to paste a K3 because you want this cycling to be 1.
Yes, that's correct. That's correct. So I do need to be careful that the discipling numbers of all these graphs is in fact 1, but all these graphs are cyclic, and so I'm in good shape. Right. And then to get this is not the general proof, of course, but I've shown you how to get from one step to the next step, and so you can just kind of rinse and repeat, just do a deduction, and if you have all the items. So you just line things up correctly. You have to do it in a more general sense, but everything's you've got all the constituent pieces. Is it okay? Makes sense. Cool. All right. We're a half hour into a 15-minute talk. So okay. So so now I'm going to switch gears and show you a sort of a different thread of research, and in fact, I'm going to show you a weaker results than Engstrom's result, which is a little bit strange thing to do, but there's a reason for it. So in another paper that they did the work, and it was posted on the archive earlier than Engstrom's result appeared, but the actual publication date was after Engstrom's result. Levitt and Mandrescu proved the bound in terms of the cyclomatic number. Cyclomatic number is easy to compute. It's just the number of edges minus the number of vertices plus the number of components. And there is a relationship between the cyclomatic number and the decycling number. So namely, if all of your cycles are vertex disjoint, then they're the same. But in general, the cycling number is at most the cyclomatic number. Okay. So the result I'm about to show you is going to be a weaker bound than what we've already proved. So Levitt and Mandrescu proved that if you take any graph, then the absolute value of the independent polynomial at -1 is bounded above by 2 different data. If you give the cyclomatic number, that is definitely a weaker bound. It is the same bound for some graphs, but it is definitely a weaker bound. Okay. Now, they also proved some other things in this paper. They proved that if you have a tree, so if you have no cycles, then your independent polynomial at -1 has the right values between -1 and 1. And they proved a weird result that gives us a little bit of a hint of what's to come. So basically, the question I'm going to be asking for the rest of the talk is, okay, we've got this result of Engstrom. It gives us a nice bound. Is it the right bound? And we're going to fumble around here a little bit to try to figure out what the right bound is. But they proved this strange bound, which is that if you have a unicyclic, so that means it has one cycle, well-covered graph. What's a well-covered graph? Well-covered graphs are a little bit strange. They're graphs in which every maximal independent set is maximum. So if you can't add any more vertices, then it has to be maximum size, right? Or every maximal independent set has the same size. That's another way of thinking about it. So if you're unicyclic and well-covered, so I should say examples of well-covered graphs are complete graphs. The complete graphs are well-covered, but you're not K3, because we know that K3 has a different -2 as its independent polynomial. And your independent polynomial -1 is between -1 and 1, right? So this is a better bound for this very special class of graphs than what Engstrom's bound gives us. Does that make sense? So these graphs definitely have decycling number 1, but then the bound gives us they're somewhere between -2 and 2, but they were able to prove something better. So this is our first clue but there is this exceptional case, and they do have to use well-coveredness, which is a pretty strong characteristic. So, yeah.
Was that proved using topological ideas? Or?
That's a good question. I don't think so, but I don't know off the top of my head. My suspicion is, so I would bet that it doesn't, but I don't know exactly I don't know exactly how they proved either of those. I can tell you after the talk if you're interested. So, okay, so as we saw in the density, I call it the density construction. The density construction is this sort of sharpness filling in all the gaps result. So we only use copies of C3 and not other cycles. And why is that? Because it turns out that if your cycle's length is divisible by 3, then you get this 2 here with some minus sign. And if your length is not divisible by 3, then you don't get this factor of 2. Okay, so for C4 and C5, you're getting either 1 or -1. So if we want graphs with large alternating number of independent sets, then somehow we want to use cycles whose length is divisible by 3. Okay, I should also say we could have used C6s or C9s as well, because so we're going to give these things a rather funny name. We didn't come up with this name. So cycles whose length are divisible by 3 we're going to call 3 tilde cycles. Okay, so we're using other people's notation here. So a 3 tilde cycle is either C3 or C6 or C9 or C12 and so on. Okay, so here's a better bound sometimes. Okay, so Cow and Wren in 2021 proved that if you have a graph that contains some cycle whose length is not divisible by 3, right, then you can get a better bound for some graphs, right? So keep in mind, so this is actually a legitimate bound for some, legitimately better bound for some graphs, because we know there are graphs where the cyclic number and the cyclomatic number are the same. And so this gives us a savings of this minus beta term, right? So we get 2 to the beta minus beta. And with actually a couple of different master's students, I spent a lot of time thinking about the proof of this is actually just the recursion. So I know the answer to that question. So they just use the recursion here. And they split it up into some different cases. But they also proved some other results using the recursion. Namely, they proved that if you are a graph with no vertices of degree 1, which is a pretty strange condition for this problem, it seems like, and you also contain a non-3 tilde cycle, then you can get an even better savings. You can get a savings at the exponent rather than okay. And Phoebe and I actually spent quite a bit of time trying to figure out what was going on here and what they were actually proving. I mean, their proofs were correct. It's just that they didn't seem to put the pieces quite together quite the right way. They used the fact that there were vertices of degree 1 in their proofs, but they didn't need to. So we were able to remove that assumption about containing a vertex or not containing a vertex of degree 1. So we were able to prove in together that if you have got a graph that contains a non-3 tilde cycle, then you get a legitimate savings for graphs where at least where the all cycles are disjoint. And the proof is easy. So
it can have always the other cycles.
Again, yeah. Which is weird. Like we didn't know what was going on. But you can have a lot of C4s, and that doesn't seem to affect the absolute value of the alternating number of independent sets. Yeah. So in fact, in this case, you need at least one. It can have other. It can have cycles of divisible whose lengths are divisible by 3. Okay. So. And we were also, I should say, like I worked on Kyle Robbins and Kyle was an older master's student, a previous master's student. He was interested in the algebraic topology aspect of things, but I was probably not the right advisor for him. So we worked on that for a while, didn't make too much progress. And then we tried to prove a density result, like Nate and I's result for this one. And what we realized is that we couldn't, at least using our constructions, there were some gaps. So, and that didn't mean that there weren't other things. There were some gaps. So I should mention Kyle briefly. But Phoebe and I were able to show that there was a density result for this for our result. So and it's the same construction as before, but yeah. Okay. So
sorry,
yeah.
when you say density result, you mean
I mean that I can hit everything. I can hit everything in the range that's given by the result. So I can find graphs who don't contain who contain a non-3 tilde cycle that get everywhere between 2 to the beta, negative 2 to the beta minus 1, and positive 2 to the beta. Okay, so Calendren also proved this result using the recursion. Which is if you've got pairwise disjoint cycles and you count the number of 3 tilde cycles and let that be k, then they get a good bound. They get 2 to the k. Okay, and also proved during using the recursion. So there were like these three results floating around, and they were different results. They used similar proofs, and we wanted to figure out what the right result was. This just seemed like they didn't quite have the right result. And so the end of the story is that what is the right result? What's the right bound? What's control? And probably you all know what the answer is, and then again, is there a density result? If I can get the right bound, is there a density result? So, okay. So we conjecture. So it did seem like the things that were affecting the absolute value of the independence polynomial -1 were the existence of these three tilde vertices. Yeah. So it did seem to only depend, like we talked about before, cycles of other lengths that weren't divisible by 3 didn't seem to affect the modulus, but the existence of these things, these three tilde cycles did. And so we defined something, we made a guess that this thing called the ternary discycling number was the right thing to use as a bound. The ternary discycling number is the minimum number of vertices needed to be deleted from your graph so that you remove all induced three tilde cycles. Okay, so if you remove all induced three tilde cycles, then that gives the minimum number of vertices needed to do that is we're going to induce here. Induced just means that if you take the vertices on that give you that subgraph, there are no other edges around. So an induced C6 means that there are no edges, no chords across the cycle. Okay, and so Phoebe and I made this conjecture that this was the right upper bound, and we knew the proof as well. Like the proof was easy. The proof you've seen already. As soon as you know what the bound is, you've written down the proof, and it's the same proof as we wrote before. It's just pick a vertex, removal lowers the ternary discycling number, and then apply induction. The only issue is that it's the base case, right? And it turned out the base case is hard, and so Nate and I thought about it for a while. Phoebe and I thought about it a while. We weren't making too much progress. We could do some things, and we weren't making too much progress. But we were saved by Google, essentially. So it turned out that there was an entirely different thread of research that was interested in exactly this the base case, and exactly this problem. So in 2014, Joe Galli, Mashalom conjectured the base case. So they said if we're going to call a graph ternary if it contains no induced three tilde cycles. Okay. And they conjectured that if you're ternary, then you've got the right bound for your independent polynomial -1. Okay? And then 6 years later, very smart people, Janowski, Scott, Alan Scott, Seymour, and Sperkel, proved the conjecture. And the proof is not, it's elementary, but it's not easy. So it takes some real work. And so, so we had our base case. And as soon as we had our base case, I should say there's been a nice thread of research generalizing this result sort of in the algebraic topology sense. Again, I'm not an expert in this stuff, but I'll just mention something. Zhang and Wu and Kim have some really nice generalizations of this to some more general settings. But that allowed us to prove the theorem. So this was a case where the proof is not the interesting bit. The result is the interesting bit. So this is a stronger result than all of these other results that I mentioned today. And it's a case of figuring out what the right bound is as soon as you have the right bound. I should say other than the base case, but you have to find the right bound and then find some very smart people who have already thought about the hard part of it. And our constructions actually give you the density result as well, because all of our cycles are disjoint, and so and they're all divisible by their lengths are all divisible by 3, and so therefore these things do their decycling number and their ternary discycling number are equal. So we got that one for free. Great. Okay. So I mean, this is sort of a problem that I haven't thought about at all, but I figure I should.
Question about the
Yes,
previous.
yep.
So can you say that any function that decreases by one when you remove a vertex gives you such a bound somehow? Like the idea is the proof by induction, where after removal of a vertex,
Yeah.
whatever phi increases by one, and then you apply the induction.
Yeah, I guess you need both some sort of like a recursion like what we had,
Yeah.
and you also need the base case to give you the right value, right? So then if you have those two ingredients, then I guess so, right? Yeah. So yeah, so I don't have great open questions, but about in this particular area, I have other open questions about sort of related things, but I think I might skip over those because the next talk is all about those. So there are lots of cool questions about the independence polynomial at one that are there's been lots of nice research here and some open questions that are still open. Something I was asked when I gave this talk at a sectional meeting, NYGTW asked about what happens if instead of thinking about just one and negative one, what if you think about other roots of unity? Then you're in some other realm that I'm definitely not an expert in, but I think it's kind of an interesting. Like, can you get bounds on the modulus of these complex numbers? I don't know. So that's my best effort as at an open question in this area. And my last two slides are about the subject of the next talk. So I read the abstract this morning. So I'm going to leave my the open question about the independence polynomial or the independent sequence of trees for the next talk. So thanks.
Interesting to think about the independence polynomial without the bounds, but for specific classes of graphs.
Yes, yeah, I think all of those. Yeah, I mean, so like these some of the areas of result, like you restrict yourself. Some of the results here restrict yourself to regular graphs, the graphs that are where all the degrees are the same, or graphs with a fixed number of edges, or graphs with a bounded min degree or max degree. Those are all questions that people thought about. I think it might be interesting to think about these things. I mean, this gives a pretty good picture of what's going on, but it might be worth thinking about it over other classes as well. Yeah,
So in the AIM polynomial research group that I earlier started, our group's project is clique sums.
Yep.
And I think pasting is like a type of vertex sum, right? Vertex amalgamation.
it is. Yep.
Or
Yep.
attaching it to vertex.
Yep.
Yeah. But it's a very specific type of it, or is it?
I mean, all I'm doing is identifying the two vertices. So in a general graph, yeah. So I drew the picture. I drew the picture as if I'm doing two roots, because I thought it looked a little bit nicer. But
you have to resolve in general.
Yeah.
Yeah. What about edge amalgamation?
Don't know anything about it. I think it's again one of these things where the polynomial is, sensitive to vertex operations more than edge operations. I mean, that probably what I said probably just now is false, but something along in spirit, I think there's.
And then your extending operation is like a vertex split, but when you're just splitting like one vertex like that.
Yeah, I mean, you could also, really, it's just a special case of pasting as well, is another way of thinking about it. You're pasting a K2 to the graph.
Yeah.
So I mean, yeah, either way, you want to think about it.
So have you thought about what independent sets look like for vertex splits?
I mean, the recursion is a little bit easier to write down, I guess. But I mean, that's kind of what we did.
Yeah.
In some sense, right? So
that's
recursion.
The general situation where you split a vertex in any way instead of this very special way you're attaching that edge almost.
I mean, if you're doing it in the middle of a graph, it's probably a much more complicated thing to keep track of. Whereas if you're hanging a leaf off of things, and it's very easy to write down what independent sets look like.
I will note that, to give you some work on this a little bit. If you take a vertex, anywhere on the graph, whatever, and try to extend it out in that graph, three vertices. So basically take it for each replacement. Reverse is just something. It's the original key value was 5, it makes it 5.
And is it 6? You get back to where you started. Is that right? Yeah. So you don't need to extend very far to get back to where you started. Yeah.
Actually, a question on the basic philosophy. It seems odd to me that you look at cycles as a way of like look for independence. I would think, I was naively approaching it, I would look for maximal cliques, because if a clique you just take one vertex for the next and putting those together in somewhat. It just seems odd. I'm not sure. I guess I'm not seeing all the proofs of it.
Yeah, I mean, I think that, yeah.
Why you're looking at the cycle.
So if you're thinking about, I think you're thinking maybe about the total number of independent sets.
Even if you're kind of odd even ones, might
Yeah.
like still you could still whatever it's odd or even, you could still take the clique, you just take one vertex in a clique or something.
Yes, but somehow the existence of these 3 tilde cycles are the things that are able to like give you more evens than odds, or like spread out the number of evens and odds. Which is weird. I mean, I don't have a great heuristic for why that's
Does it
true.
come from graph structure or from the polynomial over curve?
I think it just comes. Well, I mean, that's
Both? Okay, yeah.
The recursion comes from the graph.
Okay, yeah.
Or something. Yeah. So yeah.
I just want to make a comment to what Andrew was saying. So what's interesting to me about this is that, as you said before, like IG-1, that's the Euler characteristic of the independent complex.
Yeah.
So that is like taking all of the homology information and squashing it down to one number.
Right.
So you're losing a ton of information.
Correct. Yeah.
And it's a huge industry trying to understand the homology groups of these simplicial complexes and also find out what kind of spaces you can get from them.
Okay.
And Engstrom proved an amazing theorem saying that like you can get almost anything.
Okay.
Basically a suspension. So I just thought like what you were saying is like, oh, what happens if you do certain operations? That's actually like Engstrom and other people are investigating that. I don't think it's fully understood like how this affects the homotopy type of the independence complex. But yeah.
Awesome. Thanks for that. Yeah. I'm definitely not an expert in that stuff. So.
I have another question. Do you know if anyone's done something about independence polynomial of a hypergraph?
The only issue that I know off the top of my head is that independent sets come in different varieties in hypergraphs, just because, well, of course they do, but you have to talk about, like, in some sense, how strong an independence you want, right? Are you allowed to have a certain, like, just one vertex from every hyperedge, or all but one vertex and hyperedge, or something in the middle? So, yeah, the answer is basically, it's interesting probably, but it's probably hard, and you have to be careful about how you define your polynomial because it depends on how you're defining it.
I have a basic question because I want to understand the result. I think I forgot the definition. If you have a cycle of length 6,
Yep,
and you have no chords,
yep,
is that considered a 3 tilde cycle?
correct. Yes.
And if you have chords, it's not a 3 tilde.
So it's still a 3 tilde cycle, but it's not an induced 3 tilde cycle. So, and we only care about removing the ternary decycling number. You just need to remove all the induced 3 tilde. Those are the things that are pumping up.
So these are multiple of 3 cycles that somehow cannot have a shortcut. Right? They're
Correct.
like,
Yes.
like,
Yeah.
you can't get them smaller.
That's right. That's right.
What was your investing? We have a 8-minute break before our next speaker. And,
Should I stop the recording?
no,
Does it go?
might forget to start it. You know. Okay. Thanks for coming. Yeah, appreciate it. I guess I'll see you for. Yeah.
And is it easier for me to like email you my stuff or should I use my?
I think you can just log into your email and then that would be. Yeah. But maybe we should pause the Zoom. Let's see.